Welcome all to this lecture series on ESP32. This is fifth lecture of Module 2 FreeRTOS and ESP32. In this lecture, we will learn queue management. This lecture is mostly theory portion and from next lecture we will see the hands-on. FreeRTOS queue. A queue is a feature in FreeRTOS that allows one task to send data to another task, or it can send data to a ISR, interrupt service routine. Every queue has a fixed capacity. It can store only a limited number of items. This capacity is decided when the queue is created and cannot be changed later. Suppose we are making a queue. So the number of items it can hold is decided at the time it is being created. So this is the capacity of the queue. Suppose I have made a queue of 3 items. It can hold a maximum of 3 items only. And the size of each item is decided at the time of creation. Both the capacity of the queue and the size of each item is decided at the time of creation. Each item stored in the queue has a fixed size. It is defined at the time of queue creation. Queue works in a FIFO manner. The data which has entered first will come out of the queue first. The data can be transferred between the tasks using a queue in 2 ways. Either copy the data to the queue or pass a reference, a pointer in the queue. Queue by copy. In queue by copy, the actual data is copied into the queue. FreeRTOS makes a byte by byte copy of data and stores it inside the queue memory. This method is safe because the original data can be modified or deleted after sending. The queue data will not get modified. Queue by reference. In queue by reference, the queue does not store the actual data. Rather, it stores only the address of that data. Sometimes it may cause error as the data can be modified before it is received by the receiving task. This method is faster and uses less memory, especially for large data structure. Access by multiple tasks. A queue is an independent FreeRTOS object, not tied to any single task. Any task or interrupt service routine that has access to the queue handle can use the queue for sending or receiving the data. Multiple tasks can send data to the same queue. There can be multiple senders to the queue, and there can be multiple receivers also. But mostly there are multiple senders but one receiver. Multiple tasks can also receive from the same queue. In real applications, there may be multiple senders, but in very few cases we will have multiple receivers. When a task tries to receive data from a queue, it can choose to wait for some time if the queue is empty. This wait time is called the block time. If the queue has no data, the task is put into the blocked state. It stays blocked until data is sent to the queue or the block time expires. When another task or an interrupt service routine sends data to the queue, any task waiting on the queue is automatically moved to the ready state. If no data arrives within the specified block time, the task is unblocked automatically and the control returns to the task, indicating that the receiving operation failed due to timeout. Multiple tasks waiting on the same queue. A single queue can have more than one tasks waiting to receive data. When a new data arrives, only one task is allowed to receive that data. The task selected is the highest priority task waiting on the queue. If multiple waiting tasks have the same priority, the task that has been waiting for the longest is chosen. Blocking on queue writes. When a task sends data to a queue, it can choose to wait for space if the queue is already full. The waiting duration is called the block time. If the queue is full, the task enters the blocked state. It remains blocked until the space becomes available or the block time expires. As soon as another task or an ISR removes an item from the queue, space becomes free. One blocked sending task is automatically moved to the ready state. There can be more than one task waiting to send the data, so only one task will be unblocked and sent to the ready state. Multiple tasks waiting to write. A queue can have multiple sender tasks waiting to send data. When space becomes available, only one task is unblocked. The task selected is the highest priority task waiting to write. If more than one waiting task have the same priority, then the task that has been waiting for the longest is chosen. Blocking on multiple queues. FreeRTOS allows multiple queues to be grouped together into a queue set. A task can block and wait for data to arrive on any queue within the set. This avoids the need to continuously check each queue or use multiple receive calls on each queue. Queue sets are useful when a task needs to respond to events coming from different sources. Queue creation. The API to create the queue is xQueueCreate. It takes two arguments, the number of items in the queue and the size of each item in bytes, and it will return a queue handler if successful, or it will return a null when queue creation is failed. This failed is mostly because of insufficient memory available. Once the queue is created, the data can be sent to the queue. The sender can be any one of the tasks that knows the queue handler or an interrupt service routine. The API is xQueueSend, or it can be xQueueSend to back. Both are same. It takes three arguments. First queue handler, then pointer to the data to be sent, then block time. Block time is the time the task will wait for a queue to become empty or for a space to be available. Not empty, space to be available. If the block time is 0, it won't wait. Immediately it will return either queue full and block time is quote max delay. It will wait till there is space in the queue. Once the space is available, immediately the task will send data. Then once data is sent in the queue, it can be received by any one of the task or ISR. The API is xQueueReceive. It has three arguments. Queue handle, pointer to the buffer to store received data, and xTick to wait, the block time. This block time is the time the task will wait for the data to be available on the queue. If the queue is empty, the task will wait for the block time number of ticks. If the block time is 0, the API call will immediately return without waiting. And if it is port max delay, it will wait till the data is available. Means once the data is available, it will receive that data, and before that it won't return. And when it is returning, either it will have data, then it will return PD pass, or if it fails on timeout, it will return PD fail. So let us see how sender sends data to a queue and receiver receives the data. Sender is at higher priority and receiver is at lower priority. So the receiver is blocked as queue is empty and sender is at higher priority. Sender sends a data in the queue, and again it will send data as queue still has a space and sender it is at higher priority. Again it will send data. The queue is of size 5. So it will send 5 data. Now queue is full. Queue is full. So sender will be blocked. Now the lower priority task, receiver task, will be unblocked. Once it is unblocked, now receiver will receive the data. Now again there is a space in the queue. So sender will be unblocked and receiver is blocked. Queue works in FIFO manner. So the sender will send data at the end. Now again queue is full. Sender is blocked. Receiver is unblocked and data will move from the queue to the receiver. This way the data is transferred from the sender to the receiver. This is the case where sender is at higher priority and receiver is at lower priority. Sender is blocked when the queue is full, and when receiver receives and make space in the queue, the sender is unblocked. Let us see a case in which receiver has higher priority and sender has lower priority. So since sender is lower priority, so it will be blocked. Queue is empty, so receiver will be blocked. And since higher priority is in the blocked state, the sender, which is the lower priority task, will be unblocked. Now sender will send data to the queue. Now there is data available in the queue. So receiver task will be unblocked. And data will move from the queue to the receiver task. So like this, the queue will be mostly empty. As soon as data arrives, the higher priority task, receiver task, will receive the data, and once the queue is empty, the receiver task will be blocked. So like this, the data transfer takes place from one task to another using a queue. So from next lecture, we will see the hands-on. We will see some programs. We will create queues, send data and receive data for different cases. That's all from this lecture. See you in the next lecture. Thank you.